Hello everyone, this is Pallavi here from Team College Innovators, and how many of you are super excited and all set for today's YouTube live? I want you all to type down excited in the chat section. Okay, fantastic. I can see a lot of excitement coming in. Super. So before getting started, here are very few important ground rules for everybody for today's YouTube live masterclass, right? And so that's where, like, I'm sure that you're all going to get lot of golden nuggets values. So that's where I make sure to take your book and pen ready to take as much notes as possible, right? And also use the chat section to give your answer to the questions asked by Rajeev Sir. Okay, and also make sure to stay till the end to grab as much golden nuggets, tips, secrets on how to engineer your own motor speeds. And so that's where you're going to understand. That's where you're going to understand a lot of various different aspects of motors, torque, speed, materials, and many more. Right? So, without any further delay, let's go ahead and get started with our today's live YouTube masterclass on how to engineer your own motor space from Rajeev Sir. So, let's all welcome Rajeev Sir. Over to you, sir.
So, the context of this module is very, very simple, guys. You all want to be an EV engineer, right? And EV is such a wonderful subject which cuts across mechanical, electrical, electronics, as well as the IT. While some of the mechanical engineers, they might have a wonderful exposure to the mechanical components of it, but then their exposure to electrical and electronic components and chemical energy, especially from the batteries perspective, is very limited. Similarly, electronics guys, probably their circuits and circuit designs, etc., they are very strong, but when it comes to mechanical fundamentals, they might be struggling. And probably the IT and then the computer science engineers, maybe they are very strong with respect to the IT and programming and other things, but when it comes to the fundamentals of electrical and mechanical, maybe they might be lacking. So that's the reason the entire modules are built such a way that the mechanicals guys get the exposure of electrical electronics, the electrical electronics and software guys gets the exposure of mechanical. So that's the beauty about it. And then the way these modules are also constructed and built are such a way that they are very easy to understand. All you need to know is 8th standard physics, and from that is where we build it in, right? And now let me ask you a quick question. Are the modules being explained in the most easiest format? If your answer is yes, type yes. At least you heard a couple of classes so far. Are these being explained at the most simplest manner? Oh, fantastic. Great. So I see some direct messages. Please type it to everyone. Okay. And also, let me share. Basically, for not just any vehicle, right? For anything to move forward, inherently there are certain forces that everything has against, and that's basically called as inertia, right? You are aware, you would have heard this word called inertia. Inertia, right? Inertia means to be remaining in the same situation with respect to time as a frame. See, please understand, with respect to physics and also with respect to mechanical, time plays a very important role, because if there is anything that is constant, change is the constant. Time is the particular change. So every time we consider a parameter, we always look at the parameter, say what is the parameter at time t1 and what is it at time t2. And then the change in the particular status quo of the parameter is very, very important to us as engineers, right? Now, why I made this particular statement is because for the upcoming fundamentals that we need to understand, if you see, every fundamental thing we have derivated with respect to time. Say, for example, as I said, for us to move forward, we need to have a clear understanding of these fundamentals. The fundamentals are captured in such a way that we understand what are the mechanical or physical elements of it. And we also see what is the electrical and energy elements of it. And then we try to bring a holistic picture in understanding this. For example, we started saying distance. Distance basically is the distance is the measure of unit from one point to another point. That's the distance. And it had multiple, I would say, units. It is measured in meters, kilometers, inches, feet, centimeter, etc. But in India and in the Indian context, we generally take meters into consideration. Now, the same distance, when you derivate this against time, the derivative of distance, that means at time t1, an object is here. At time t2, the object is at a different place. This t1 minus t2 is basically your a change in the distance between these times is where you get the speed or velocity. The fundamental units are definitely kilometers per hour. That is what we see on our vehicles. But then for all most calculation purposes, we use meter per second as the fundamental unit. And then we have acceleration. Now, the speed is also not constant. Say, for example, at some point of time, you might be driving at 40 kilometers per hour. Probably in the next, I would say, fifth 5 seconds, you might be traveling at 50 kilometers per hour. That means there is a change in the time frame of 5 seconds from 40 to 50 kilometers per hour. So this 50 minus 40 by 5 seconds basically becomes your meters per second square. That is acceleration. That is the derivative of speed. The rate of change of speed is called acceleration. Now, until then, we have heard the fundamental elements of it without any entity. Now, whenever you call an entity, the entity brings something along with that. What is that? The entity brings mass. Assume this as your car, right? Now, we have learned distance, we have learned velocity, we have learned acceleration also. But when an element or an entity starts acting upon it, it brings along with this a particular function or a parameter or inherent property called the mass. Now, when this particular element with that particular mass starts moving at an acceleration, then the element is being subjected to a force. And that force is basically nothing but the mass, the mass of the element and then the rate of change of velocity. That means mass into acceleration. Kg meter per second square is also called as Newton. Why Newton? Because Newton is the one who first invented this particular element or a gravitational force when he was sitting under the apple tree. You all know the story. An apple fell down. Then he was wondering why an apple fell down, because then he understood that the earth has got an inherent gravitational force, and that we have seen to be around 9.8 meters per second square. So any element that has got a mass of, say, for example, 10 kg, then the gravitational force that is generally exerted on that particular element is 10 kg into 9.8 meters per second square. So roughly 100 newtons or 98 newtons, right? That's your fundamental understanding. Now, that's the force that is exerted upon this vehicle or that object. Now, because of the force that is exerted upon, the object also makes a movement from again point A to point B. Now, because of the force exerted, the object with the inherent parameter or with inherent quality of mass, because of the force exerted, it has got a force of mass into acceleration. And this mass into acceleration, this force resulted in the object in moving from point 1 to point 2. And this change in the distance, when you multiply that with particular force, that is what basically is the work done on that particular object. That is what you call as work done on that particular object. Now, we have understood force, we have understood work. Now, in how much speed is this particular object moving from point A to point B? That is, the derivative of that work is basically what is called as power. And then the units of power are watts or joules, joules per, I would say, second, right? So until now, you have understood. Now, then there is another world, another realm. So far, we are only talking about a linear realm. Then there is also another realm called the angular, the circular, or the radiant realm or rotational realm, right? Rotational realm is something we said, right? If at all there is a block, you push that block, that is linear. If it is a door hinged at one point, and then you push the door on the other point, then the movement of the door is angular. That's the angular world, right? So when we entered into angular world, we said that torque is an indication or a reflection of force, right? Force is in the linear motion, torque is in the angular motion. Now, how do you define the torque? Torque is again defined by the point at which the force is applied multiplied by the radius from the pivot where it is rotating. Say, for example, if you take a hinge, a door of say 1 feet or a 0.5 meter, right, or 2 feet or a 0.5 meter example, right, and then you started applying a 3 Newton 3 Newton force, right, at the hinge. Now the torque that is acting through Newton force at the end of the door. Now the torque that is acting upon that particular door is this 2 cross that particular radius where we said it 0.5 meter. So that is roughly 1 Newton meter becomes the torque of it. Now again, in terms of linear distance, it is simple distance that we have measured. But in terms of angular distance, we always call it as the radians, right? Radians or degrees are the units in which the angular distance is measured. So basically, if there is an angle that it has, say, for example, let me take a quick the angular perspective of the linear distance is nothing but the angular distance or radians or degrees, and 3.14 radians pi is equals to 3.14 radians, that is how it is defined, is equals to 180 degrees. This we are going to learn even more in detail, but for now understand this. Now the angular concept of the linear velocity is nothing but angular velocity. It is generally represented by omega, and again this is again radians per second. That is how the angular velocity is represented. Now, until now, what we have learned are, we have learned the physical elements from the linear perspective. We have learned the fundamentals from the angular velocity and angular realm perspective. And now slowly we digress that into the electrical at this point of time, and then we see how these both merge. Okay. Now, when it comes to electrical components, and electricity is nothing but movement of electrons. And by convention, since electrons are negative, the movement of electrons in one direction, I mean, electricity is always considered in the opposite direction of the movement of electrons. And how do electrons move? Electrons, I told you last time also, you need to consider this more as a waterfall. A water falls from a higher altitude to a lower altitude. Similarly, and electrons always flow from the higher altitude, that means high dense to low dense. Now, this particular difference between these 2 points through which these electrons move is called potential difference or voltage difference, which is represented by a unit called volts, V volts. That's called the potential difference. Now, because of the potential difference, the movement of electrons is represented by a unit called ampere, and that is generally represented as I. Now, as again, even in terms of the mechanical realm or in terms of the electrical realm, there is something which is always given. What is that? That is friction. Because even if I were to push this particular thing, there is a frictional force. It has to overcome the static friction, and then it enters into a dynamic friction mode, right? So there is a friction that is always playing a role, and then the friction in terms of the electrical components. Say, for example, even if the electrons, you facilitate a copper wire between the potential difference. Say, for example, you have this battery, right? When you take a battery, you have a positive terminal and you have a negative terminal, right? Now, when you take a wire from positive terminal and before connecting it to the negative terminal, you put a bulb in between and connect the rest of the wire to negative terminal, the bulb glows. Why? Because the electrons flow through the positive terminal to negative terminal. Now, during this flowing of electrons, the copper wire also has got certain resistance in it, and this resistance is basically called as ohms, and that is because of this resistance only you also find a lot of heat being generated during the movement of the electrons. So are you clear until now in terms of resistance and friction, ohms? If you are clear, type yes, it is clear. I'm quickly revising because past class I have spent a lot of time on this particular table, but this time I do not want to repeat the whole thing, so hence I'm revising quickly. Now, similarly, the power in terms of the electrical context is the potential difference that we spoke about. When it is multiplied by the quantum of current that is passing through, that becomes the power of that particular energy source. That becomes the power of that particular circuit, right? The potential difference V multiplied by the quantum of current that passes basically becomes the power. And energy is how long does that power sustain? How long that power sustain? Because see what happens, it is like this. when the electrons start moving from the place of higher potential to lower potential, what happens at one point of time, the potential difference almost becomes zero. The gap between both the terminals becomes zero. That is when you call the battery is exhausted. How do you call the primary batteries? Primary batteries means, I'm going to talk about all of this later, but for now, take them as primary batteries. How do you call one particular battery is dead? That particular battery is dead because the difference, the potential difference has become zero. That means all the electrons that were there at the positive terminal completely started flowing towards the negative terminal until the potential difference between them became equal. And once the potential difference becomes zero, there is no movement of electrons, right? And that means there is no power. So now, over how much time does it take for this complete power to be dissipated? That is basically the energy unit, right? The power multiplied by time, right, becomes the energy unit. Are you clear until now? Shall we move forward? See, the reason I engage and then I ask you to keep typing is so that you stay engaged to the class. Yeah. Okay. Now, this is again another fundamental example through which I really want to again talk about it, right? So you have a dumbbell of 2 kg, right? I'm not sure. I'm sure if people exercise, they generally exercise with 5 to 10 kg. But then for our experiment and an easy understanding perspective, I've taken here a 2 kg dumbbell. Now, when the 2 kg dumbbell lies on the road or lies on the floor, what is the force that acts upon it? It's the gravitational force that acts upon it. That is 2 kilos into 9.8 meters per second, which becomes close to 20 kg meter per second square, 19.6 or 20 newtons. Now the dumbbell is here. Assume this is the dumbbell and this is there on the ground. Now this is the dumbbell. Now, for me to lift it, what is the minimum amount of force that I need to apply to overcome? To lift it from the ground, what is the minimum amount of force that I need to apply to overcome? Quick answers, please. What is the minimum amount of, quickly type them in the box. What is the minimum amount of force I need to apply to lift it, to start lifting it from the ground? Absolutely correct. 20 newtons. Karnati said 20 newtons. Correct. You will need to apply any force a little more than 20 newtons, and then you will be able to overcome the gravitational force that is pulling it. Now, imagine you lifted it by 2 meters. You lifted it by 2 meters. Now the dumbbell is at a 2 meters height from the floor. Okay, the dumbbell is at a 2 meter height from the floor. Now, what is the work done on the dumbbell? Force into displacement, right? What is the work done on the dumbbell? It is 20 newtons into 2 meters. That is roughly 40 joules. Now tell me, this dumbbell at this 2 meters height, what energy does it carry? Let me repeat that question. That dumbbell of 2 kg, when you have lifted it by 2 meters from the ground, what kind of an energy does it carry? What is the name of the energy that it carries at the 2 meters height? Come on, guys. You would have prepared for IIT, JEE, MSET, AAEE. You should know all of this. Quickly type. What is the energy that the dumbbell is carrying at a 2 meters height? Okay, let me give you a clue. The energy's name starts with P. Oh, finally. Great. Abdul and Narish. Fantastic. So the dumbbell at that particular point is carrying a potential energy of 40 Newton meter or 40 joule. So the work that you have done is stored up there as a 40 newtons work. Now imagine you picked up this 2 kgs dumbbell until 2 meters height within just 2 seconds. Then what is the power that you exerted upon it? The power that you have exerted upon it is 20 watts. This is a physical representation. This is a physical representation or a physical understanding or an experience of all the, I would say, concepts that we have learned so far. Is it clear? Shall we move forward? Okay. Then we also quickly looked at what are the 3 different forces that act against a vehicle, right? Let us assume that the vehicle is at an inclination, then of an angle called theta. Then we said there are 3 main forces that act against the vehicle. Number 1, the drag force, or you also call as the aerodynamic force that acts against the vehicle. Number two, the rolling resistance. The wheels that roll also have to overcome particular resistance. And number three, we also said the gradient force. Gradient force is the force that is acting upon the vehicle because of the delta or a theta. So we also said, how do you calculate the theta? Theta is nothing but the end of the road, the height of the particular road, the width of the particular road by the total length cross section of the road. That is P by B becomes your theta, or tan inverse of P by B becomes your theta in gradients. But that's not too much of an important to us. What is important to us is rolling resistance is mu mg cos theta that acts along the tires, and then the uphill resistance is mu mg sin theta, climbing force. So that's where we said, right, if this particular theta that we have right here, I'm not getting the pointer, just a minute please. So do you see my mouse movement, guys? Yeah. So if this theta is to become 0, that means there is no inclination at all. Is there any climbing force that is acting against it? Should the vehicle has to overcome any climbing force? No, right? Because mg sin theta, when theta is 0, that becomes 0. Similarly, imagine if this particular theta becomes, say for example, 90 degrees, right? 90 degrees means it is almost like an uphill wall, right? The theta right now, which is here, it kind of becoming 90 degrees. Now, when it becomes 90 degrees, and do you think there is any rolling resistance acting against the vehicle? The vehicle simply slips, right? So rolling resistance is mg mu cos theta, and climbing force is mg sin theta. Mu is nothing but the rolling coefficient. So are you clear until now? Yes, this we have explained very much in detail in the last class. So I'm hurrying so that we can cover the new concepts faster. So finally, the aerodynamic force. Aerodynamic force basically depends upon the cross-functional area of the vehicle that it is exposed to. That's why you see, when you compare two-wheelers, three-wheelers, four-wheelers, and a lorry, on a lorry, you have a greater aerodynamic force. And that's the reason, if you look at F1 race and F1 cars, etc., or even the sports cars, their contours or designs are made such a way that they experience least aerodynamic force, right? And how is this aerodynamic force calculated? It is half rho CD AV square. Now, rho is nothing but the density of the air, which is 1.1 kg, 2 kg per meter cube. I told you how do you calculate the density. Density is nothing but mass per volume. You take 1 cubic meter of box, and then you fill with air until the brim. Then the measure of that particular quantum of air that went into that cubic meter cuboid or cube becomes your density. And here it is 1.2 kg per meter cube. And then area is the frontal area that is there. And then V is the velocity at which the vehicle is traveling. And the drag coefficient is CD. Now, we are not necessarily getting into the derivation of this formula for a simple reason that we are here to apply these fundamentals into our things. We are not doing a PhD in physics trying to understand how we arrived at density is equals to 1.2 kg per cubic meter or rest of the things. What is important? We learn them logically quickly and then we start applying them. Are you here with me until now? Yes or no, guys? Come on. Let's continue. So it is at this point of time is where I have given you an assignment. The assignment that I've given you is this. There are three kinds of vehicle portfolios: a two-wheeler, a three-wheeler, and a four-wheeler, with different coefficients of friction and coefficients of drag. So CD at 0.9. For three-wheeler, it is 0.45. And for four-wheeler, it is 0.3. Then the frontal area also I've given 0.6 square meters, 1.6 square meters, and four-wheeler 2.5 square meters. The gross vehicle weight is around 200 kg, 600 kg, and 1500 kg. Mu is equals to, again, the coefficient of friction, which is 0.015 for all of them. Tire radius for two-wheelers is 0.28 meters, three-wheelers is 0.2 meters, and four-wheelers is roughly 0.3 meters. Velocity V1 is 30 kilometers per hour, and V2 is 80 kilometers per hour. I told you to find out all these three forces: the aerodynamic force, the drag force, as well as the rolling resistance at both these velocities, given the angle of inclination is theta is equals to 8 degrees. Let me stop presenting and share another screen. Yeah, can you see the screen, guys? So we have two-wheeler, we have three-wheelers, we have four-wheelers, we have all the parameters that have been put in. V1 is equals to 830 kilometers per hour and V2 is equal to 82 kilometers per hour. Now, what is the rolling resistance? What is the formula for rolling resistance? Mu mg cos theta, right? So here in this case, cos 8 degrees is around 0.99. Mu, that is the coefficient of what is it that is given? Mu is given as 0.015. So 0.015 into cos theta is equals to 0.99 into mass of it is 200 grams, 200 kgs, and into G is 9.8. So my rolling resistance is mu mg cos theta, that is roughly 29 newtons is my rolling resistance. And for three-wheelers, it is again, the only thing that is changing here is just the weight. Rest of the things, mu is same, mass is the one that is changing, cos theta is again the same. So the rolling resistance that is acting against a three-wheeler is around 87 newtons. Okay. And the rolling resistance against four-wheelers, again, cos theta, that is 0.99 into mu 0.015 remains the same. And that is multiplied with 1500 kgs, it becomes 218 newtons as the rolling resistance that acts against these two-wheelers, three-wheelers, and four-wheelers. Now, gradient resistance. Gradient resistance is mu mg sine theta. So grading resistance of mu mg sine theta is, one second. Yeah. So the rolling resistance is mu mg cos theta and grading resistance is only mg sine theta. It is not mu mg sine theta. So it is mg sine theta. Now sine 8 is again 0.14. G is 9.8 meters per second square. And again, D2 is the mass of it. So mg sine theta is basically is your gradient force. And your mg sine theta, that is gradient resistance that is acting at an 8 degrees is really, really high. That is around 274 newtons, 823 newtons, and roughly 2000 newtons in terms of four-wheelers. Okay. Now, you have rolling resistance calculated, you have gradient resistance calculated. Have your answers also in line with this? Can you please respond? Dear friends, whatever you have worked out in the last assignment, are your works in line with this? Kindly mention. So we have rolling resistance and gradient resistance. Rolling resistance again is the resistance that acts against the rolling of the tires, and gradient resistance is again something to do with the ramp at which the vehicle needs to go. Now the most important thing is aerodynamic resistance. Now when the vehicle is at a constant location, okay, somebody says with 0.5% error, that's okay. Now let me ask you one question, guys. The vehicle is standstill, it is not moving. Assume this is the vehicle and this is standstill. What is the aerodynamic force that is acting upon it? The vehicle is there and it is standstill. What is the aerodynamic force that is acting upon it? Quickly. Yeah. Sai Kamal says 0. Why? Because it is, as long as there is no movement, when the velocity is 0, your aerodynamic resistance force is half rho CdAv square, right? So that you see that here, half rho CdAv square. So at velocity 0, that means when the vehicle is about to start, there are only two forces that act against it. What are those two forces? One is the rolling resistance and gradient resistance. That means the traction that is required to produce by the traction motors in terms of electric vehicles. Because in electric vehicles, we saw the components of electric vehicles last week. We have energy house called battery, and then we have movement, the vehicles that the components that enable the vehicle to propel or move. Those are called traction motors. The energy from the traction motor is transferred to the motors through controllers. Those are the controllers which control everything. That's what we learned last week. So as long as the velocity is zero, only two forces that are required to overcome that are required by the vehicle to overcome to initiate that particular movement is rolling resistance as a force and gradient resistance as a force, or a climbing force. Now, at velocity is equals to 30 kilometers per hour. So this is how the aerodynamic force is. 30 kilometers per hour, it is going half 0.5. Your rho is 1.2 kg per meter cube. That is the density of air. Your CD, that is coefficient of drag for two-wheelers, it is around 0.9 because it is. Then the area, the area is again 0.6 square meters for two-wheelers, and then the velocity is roughly, I would say, sorry, the velocity is 30 kilometers per hour. So when you do the entire thing, the aerodynamic force that is acting against the vehicle is roughly 23 newtons on two-wheelers, 30 newtons on three-wheelers, and 31 newtons on four-wheelers. Now it is very important. That's what you find, right? When you go at a lower speeds of 30 kilometers, etc., 30 kilometers per hour, etc., you are very, very comfortable. Now, the minute you accelerate, you throttle and take it to 80 kilometers per hour, what happens, guys? Quickly tell me. Quickly tell me, guys. When you accelerate it to at 80 kilometers per hour, what physical observations happen to you on the two-wheeler? Yeah, the kilometers per hour have to be converted into meters per second. Perfect. Yeah, high resistance, right? Your eyes would start watering, your hair goes like this, your shorts, your t-shirts, they all go. Why do you think that's happening? It is just 30 kilometers to 80 kilometers is just almost, you grew by only 3 times the speed, right? 2.7 times, 2.6 times the speed. But why so much of an air resistance? Tell me. Quickly. There is a reason. Why? Very brilliant, Sai. Sai, don't direct message. You message to everyone. Sai rightly said, because if you look at the aerodynamic resistance is equals to half rho CD A V square. That is, the aerodynamic resistance is directly proportional to square of the velocity. So even if the velocity grew only by say 2.5 or roughly 3x times, then the resistance almost increased by 3 square, 9 times. That is why you see, that is what you also experience. So with the change in the speed, your rolling resistance doesn't change, your gradient resistance doesn't change, but it's only your aerodynamic resistance that changes, and it really changes by the square of it. Now let's go back to, are you clear until now? So those who haven't done the assignments, at least now you look at it and then do the assignment. Yes? Can I get a yes? Okay. Let's continue. Let's continue. So we will go back to the same presentation. Okay, guys, can you see me? Is right? You're able to see me, correct? And you're also able to see the screen. Okay. Now let's continue. So this is what we have seen, right? This is what we have seen. We have calculated the rolling resistance. We have calculated the gradient resistance. We have calculated the at a smaller velocity as well as at a higher velocity. Now the interesting insights, what we saw for ourselves is, this is the interesting insights. The interesting insights that we have seen is very, very simple. We saw that aerodynamic force or drag force changes to the square of the velocity, and hence higher the speed, more the aerodynamic force. This we have seen clearly. Now let's continue. This is very important. Now let's arrive at this particular calculation. Now you have rolling resistance captured, you have gradient resistance captured, your aerodynamics at lower velocity and aerodynamics at a higher velocity. So now, what is the traction force that is required to overcome? So now this is our traction force. Now, what is this traction force? This traction force is nothing but at the initial velocity, right? At a traction force for a 30 kilometers per hour, you add this up 30, 23, 53, and you add this particular thing. It is roughly 326 newtons. Similarly, the traction force required would be 941 and 2300. And yeah, okay. So that's the traction force. So there are multiple, I would say, traction forces here. Let me clear this particular thing. Multiple traction forces for the vehicle to start moving at velocity 0. These are the traction forces the vehicle has to overcome. And then at 330 kilometers per hour, these are the traction forces the vehicles have to overcome. And at the 80 kilometers per hour, these are the traction forces that the vehicle needs to overcome. This is for two-wheelers, three-wheelers, as well as four-wheelers, right? Now, how did we get this traction force? Simple. At velocity is equals to 0, gradient force plus aerodynamic force alone. That's why it is only just the summation of these two. So again, this is just the summation of these two. And again, this is just the summation of these two. Now, at velocity is equals to 30 kilometers per hour. The velocity is equals to 30 kilometers per hour. Then you sum up the V1 at 30 kilometers per hour aerodynamic resistance and V2 at 80 kilometers per aerodynamic resistance. And that is how you will start getting the traction force. Now, though I have solved this for you and I have kept it for you, I want you to repeat this particular this exercise. I'm going to explain the same thing in detail now. Now that you got the drag force, you got the rolling resistance, and you got the climbing or a gradient force, the gradient force plus rolling resistance and then the drag force, all these three put together must be overcome for the vehicle to move. And this force, which is required to overcome all these three, is basically called as the traction force of the vehicle. Are you here until now? The traction force of the vehicle, the traction force of the vehicle. Are you here until now? Are you here with me? Please respond. It's very, very important, this particular concept, which I'm going to explain right now. Okay. Now, imagine this, guys. We looked at the conversion from the linear motion to rotary motion. Yes. Have we looked at it? Okay. Now, what is the now if the vehicle has to move in a tractional in a linear motion, does the vehicle skid or the wheels rotate? Tell me. When you drive the car, the vehicle doesn't skid, right? It is not like this ice skating where it goes by skidding, right? The wheels rotate, the wheels turn, and then the vehicle moves. Now, for the wheels to turn, this particular force, what you are expecting, the traction force, needs to be converted into torque, which will enable the wheels to turn. Are you here with me until now? Okay, so now how do you arrive at the torque that is required by the motor? Because end of the day, what happens? Assume this as like this. Assume it is a hub motor. Hub motor means there is a motor at the center of the wheel. Okay. Now, if the vehicle has to move at a particular force, then the motor has to produce a torque which is equivalent to that particular force. And how do you calculate? You calculate that because the hub motor is at the center of the wheel. The torque requirement on the hub motor is the radius cross force. Okay, now this is very important. Some of you from this batch reached out to me saying that there was an event called Baha that is happening in SAE and we built an electric vehicle. Okay, then I have asked them, how did you arrive at the motor that you have required? What are the calculations you have done? And then friends are very, very honest and good. They said, no, we didn't really do any calculations. We went to the market, picked up a good motor that is available from a good company, was the answer that I received. This is how you calculate, right? Suppose if you're building a four-wheeler, if you're building a three-wheeler, if you're building a two-wheeler, those fundamentals I've already given. What would be the coefficient of drag? What would be the coefficient of friction? What would be the rough frontal area? This is how you arrive at the force that is required, and this is from where you calculate the torque required. Now, for any motor that you buy, there is one specific curve that you need to see. What is that curve? Before I buy any traction motor, there's one specific curve that you need to see. Any understanding what that particular curve is? The curve is torque versus power curve, which we are going to talk about it. But as part of which, for the first time, as right now for the information, let us assume that we are only we are only calculating the torque. So the torque at the vehicle, and here I'm assuming it to be a hub motor. So there is no gear ratio, there is no efficiency. Let me assume just to be one. So torque at wheel is nothing but torque at motor. So your torque motor is nothing but R cross F, right? That is what torque as a vector. It is your radius of the wheel cross the traction force. So this is how you arrive at the torque that is required by the motor so that the vehicle moves. How many of you understood this particular theory until now? Quickly type, yes, I have understood. Is it easy for you to comprehend and understand? No complications, right? Torque, force, radius, power. My goodness, what are these terms? Right? Probably some of you would have thought like that, but it need not be in that fashion. So, see, slowly we are building up. Are you able to notice it? Slowly we are building up. So earlier we calculated the rolling resistance, then we calculated the gradient resistance, then we calculated aerodynamic resistance at 30 kilometers per hour, then we calculated aerodynamic resistance at 80 kilometers per hour, then we got the traction force at velocity is equals to 0, we got the traction force at 30 kilometers per hour, we got the traction force at 80 kilometers per hour, and then the radius here, in this case, the radius of the wheel I've given 0.28 meters. Now you got the torque of the motor that is required when you multiply that particular thing with the say for example this is basically at 30 kilometers per hour. The torque we calculated is exactly 30 kilometers per hour. So you multiply this traction force into the radius, and that gives you this particular torque of the motor. Are you here with me? 91 Newton meter, 188 Newton meter, and four-wheeler is 692 Newton meter. Are you here with me? Yeah. So now this is going to be very important, because it is from this. See, what we are actually calculating at this point of time is, for if my vehicle is an electric vehicle, and for this vehicle to overcome the mechanical forces that are acting upon it, I am basically arriving at the torque and then the power requirements of the motor. This is basically called as drive motor or a traction motor. Now what we will do is, once we arrive at the torque power combination of the motor, then we will arrive at the energy requirement. What did we say? Power and energy relation. What did we say? That power, if it is sustained over certain particular amount of time, that power into time is energy. That's what we learned. Do you remember, guys? The power at the highest, say for example, the motor is very, very powerful, right? Say for example, it's a 4 kilowatt motor or 2 kilowatt motor. How long this motor would continue to run at the highest capacity of say 4 kilowatt? How long will it run before my energy completely gets depleted? And that becomes your energy. Now, how long should it run? When you decide the T factor, the time factor, when you say that it has to run, say for 3 hours or 4 hours or 5 hours, when you multiply that 4 kilowatt motor into 4 hours, that is where you get a 16 kilowatt hour energy. And from the 16 kilowatt hour energy, you get the specifications of the battery. Is it clear to you, or shall I repeat? Please respond. Let me repeat again. So far, you have taken 3 different kinds of vehicles, 2-wheelers, 3-wheelers, 4-wheelers, for your understanding. You looked at different forces that are acting upon it. right? These are all fundamentals. Then you summed up all those forces and said, if my vehicle has to move, my traction force must be minimum more than this. So you arrived at the torque. Okay. Now we will also calculate the power with respect to torque. Then you have a torque versus power curve. That means you have torque and power requirements for your motor, and you will pick that torque power motor combination. Now you've got the power train or a drive train or a traction motor combination that is required for your vehicle to move. Now what you're going to decide is you're going to decide your fuel tank. This power you will convert into energy, and according to that energy is where you choose the battery. Are you clear with me, guys? Come on, quickly. Yeah. See, now, this in general, this particular multiplication of gears, gear multiplication torque, I really do not want to take this in detail, but let me quickly explain it to you more from the practical perspective. Now, why do you have gears in the vehicles? Simply tell me, why do you have gears in our two-wheelers, three-wheelers, four-wheelers? Quickly tell me, guys. Transmit power to adjust speed and torque. Manidi, correct. Let us assume, see, as soon as you start your two-wheelers or as soon as your start your, I would say, four-wheeler, generally you will see 1500 RPM or 2000 revolutions per minute kind of an indication, right? Your engine runs at that particular so many revolutions. One revolution, so such revolutions, 1500 revolutions per minute. Example, well, so 1500 divided by 60 is roughly how much? 25 revolutions per second. Correct? So second, 25 revolutions. Second, 25 revolutions. Now imagine this. When your engine is rotating at that particular speed, if that engine is directly connected to your wheels, what will happen? Two things will happen. One, if the wheels and the vehicle is too strong for the engine to overcome, the engine stops beating and the vehicle stops. Or as soon as that is done, the engine, the wheels kind of twirl or skid at the same point and then they run, right? So for that 1500 revolutions per minute, for it needs to be transmitted to the wheels. Now, how should it be transmitted to the wheels? Let us assume that your engine always runs at 2000 RPM. This is just for an assumption. Let us assume your engine always runs at 2000 RPM. So if the engine is continuously running at 2000 RPM, your vehicle demands are different. When you start your vehicle from velocity 0, you need more force. And when your vehicle already moves, you don't need so much force. I mean, when you have to increase the speed of the vehicle at the same 2000 RPM, you need more revolutions at your wheel compared to this particular engine. So at high, if at all you want to achieve higher speeds, you need gear multiplication and correct. If you want to really start, then you again need a gear multiplication such a way that you will gain more torque at the beginning. Now, this change in the demand of the vehicle demands a transmission from engine to the wheel, and that is basically called as transmission, also called as transmission gear system, also called as a gearbox. What does this gearbox do? This basically gearbox is set of gears that are engaged. I'm going to bring a specific video or slides at a later point of time where I will show how a complete transmission box looks like. So it is set of gears that are engaged so that the RPM, which is the input of the engine, will be converted and given as a feed or an output to the wheel as per the need of the vehicle. Even at 2000 RPM, at the beginning, majority, see what is power? Power is equals to, what is power, guys? Power in angular world. Power is equals to torque into angular velocity, correct? Yeah. So assume that the power is constant, right? and you need more torque. So if the power is constant, torque is inversely proportional to the velocity. So at the starting, where you need more torque for the vehicle to move, your gears will be arranged in such a way that that 2000 rpm will be reduced and given to you, so that you will have, so that means, say, imagine the 2000 rpm of the smaller gear will be connected with a bigger gear. So for multiple revolutions of this particular thing only rotates a particular only a fraction of the rotation that will enable the vehicle to move. Similarly, at higher speeds, when you really do not need so much of torque, then what happens is you will either that particular, for one revolution, you will ensure that you will have smaller gears, where for one particular revolution of it will at least multiply 1.5 times or 2 times. So this I'm going to talk in detail in the transmission of the vehicle section. But for now, understand this particular thing. So what is it we said? The torque. One second. Sorry, 1 second, guys. Hello, are you able to follow? Are you here with me? Okay. So for now, assuming that the gear ratio is same, right? Our vehicle torque and engine, right? Vehicle torque and vehicle RPM. Vehicle torque and engine torque, we are assuming it to the same, assuming it to be a hub motor. There is no gear ratio. That's a good question. Do we have gearbox in EVs? I'm going to answer. So there are multiple constructions of EVs, my friends. In certain EVs, there is no gearbox. Say, for example, most of the times in two-wheelers, etc., it is directly the hub motor where this power and torque curves are controlled by microcontrollers or processors. So they will take, the programming will take care of all of this. In certain cases, there is a transmission, but not necessarily through a complicated gear structure like that of an ICE vehicle, but it's a simple one-step gear, right? So there are both constructions that are available, possible in the vehicles. Okay. So we already read this. Assuming that the power of the vehicle remains the same, torque and velocity are inversely proportional. Gear is required for ICE engines, but for motors, the change in the gear is not required, and hence a single gear is sufficient, right? That's what I told you. Because majority of this is controlled electronically through the right smart intelligence programming. Let's continue. Okay. Now this is very, very important, guys. Come on, please focus here. So power is equals to torque into angular velocity. Okay. Yeah. Power is equals to torque into angular velocity. Now, what is angular velocity? Angular velocity is nothing but speed of the vehicle by the radius of the tire, correct? Angular velocity at the hub of the motor, at the center of the wheel, at the hub motor. What is hub motor? You have a wheel like this, and you have a motor here, right? At the hub of it. This is hub and these are the spokes, and this is called hub motor, right? So this is the radius. Okay. Now, this is called angular velocity. This particular revolutions per minute is basically called as angular velocity. And this linear velocity of the vehicle is called the linear velocity. Are you here with me? Are you able to understand what I'm trying to communicate? Right? Are you able to communicate? Are you able to understand, guys? It is very simple, right? There's no complication. Okay, now simple. I understand your questions. In EV, can we use manual gears? See, when it comes to a question called can we can, but then do we need is something we need to answer, because EVs are really smart. I mean, when you control everything with the right, I would say, circuits and right programming place, why do you want to manually change too many things? That's the problem. That's the question I want you to understand. Okay, and please ask these questions to all so that everybody will get benefited, not necessarily directly to me. Are we too late? Okay, let's continue. Are you here with me, guys? Right? So assuming that, again, let me repeat this. This is very, very important for you to understand the fundamentals. Even during the interviews, if at all you are able to focus and then explain these things in clear, let me tell you, your interviews are done. So assuming that, say for example, we have a cycle. I'm very bad, but let me quickly assume that we have a cycle and we have two wheels here. Let's assume it so. This is the seat. And this is an electric cycle and you have a hub motor at the center. Okay. Now, this cycle is moving at a linear velocity of, say for example, 10 kilometers per hour. Okay. Now, this linear velocity needs to be converted into angular velocity at the motor. Now, that angular velocity is nothing but this linear velocity divided by the radius of it. This is the radius. Perfect. Somebody wrote V is equals to R omega. Correct. Omega is equals to V by R. Both are the same. Right. So now understand this. The power is same. So the power of the motor is the torque of the motor into the angular velocity. Okay. Now understand this. So what is the value units of power? Watt is equals to torque into V by R. Now why this V by 3.6? When you convert this angular velocity into linear velocity, 3.6 is the factor that comes in, which I'll explain in the coming slides. Right. So power is equals to T into V divided by 3.6 times of R. Are you here with me until now? Yes or no, guys? Are you following me? This basically V is equals to R omega. We converted that omega into V by R. Okay. Now understand this very clearly. This power, what is the unit of power? Watt. Okay. This power is watt. And what is the unit of this velocity? The unit of this velocity is kilometers per hour. Okay. Now look at this. Now I am bringing this particular velocity here. That means P power divided by velocity is giving me torque of the motor into torque of the motor by 3.6 R. Are you here with me until now? Guys, every step is important. So please respond if you are able to follow. Yeah. Now, what is this units of power? The units of power is watt. What is the unit of velocity? What is the unit of velocity? The unit of velocity is kilometers per hour. Okay. Now, when you put this rightly, how that it becomes? It becomes watt hour per kilometer. Am I right? Correct? No, this kilometers per hour, this R gets into the numerator. So basically, P by V units is nothing but watt hour per kilometer. Are you here until now with me? Are you here until this particular step? Okay. Now, this watt hour per kilometer is nothing but watt hour is what? Watt into hour. What I told you, watt hour is the power into time. Is what? What is watt hour? Power into energy, correct. So the watt into hour is nothing but energy required to cover 1 kilometer is one way of showing it. The other way of showing it is power required for 1 kilometer hour speed. Are you here with me? Energy required to cover 1 kilometer, or power is what? Derivative of energy. Power required to cover, power required for 1 kilometer hour speed. Are you here until now? So now understand this. Your power by velocity is equals to torque by 3.6 R. Okay, do you get this particular statement? Yeah. Now, are you here with me? Are you here with me until now? Now look at this very clearly. This power, which is watt hour per kilometer or watt per kilometer hour. One second, guys. Yeah, sorry, guys. Now understand this. The power consumed is directly proportional to what's it? 3.6 is a unit. Let us assume the radius of the tire will not change. No, while you're driving, radius of the tire will not change. So these are all constant. So your power consumed is directly proportional to what? The power consumed or battery drained basically depends only on the torque. So that's why you apply more torque, the battery gets drained faster. Are you here with me? Guys, these are very, very fundamental and they become building blocks for the rest of the course that we are going to move forward. So it is very important for you to understand this, and I have tried my best to simplify this as much as possible. I can give you a guarantee. I was also a Sri Chaitanya student like many, and I was in the ICU batch, intensive care unit batch. Even best of my physics professors never taught me the concepts of force, energy, power, torque in the way that I'm teaching you. Because the difference is those professors were only from the academic background, but here I was able to design vehicles. My first job was with TVS Motors Company as a design engineer, and I had to bloody know all of this while designing my two-wheeler. That's the difference when a person from industry teaches versus the person from only pure academia. Not undermining any professors, but I'm only trying to build the difference. Are you here with me, guys? Absolutely. So somebody clearly mentioned at given power, torque is inversely proportional to the speed. If the power is same, if the power is constant, that's what we learned in the previous thing. No, that's why this torque and power curves, operating the motor in the torque and power curves is very important for better efficiency and for better life of the motor. Somebody rightly said, yes, again, don't send just direct messages to me, my friends. Send it to everybody so that everybody says, yes, power is proportional to torque, and at a given power, torque is inversely proportional to velocity. You're right. That's what we have seen in the previous thing. Shall we continue? Yeah, let's continue. So, from vehicle speeds perspective, right, from the vehicle, the speed at which the vehicle is moving, we arrive at the angular velocity of the wheel. How do we arrive at the angular velocity of the wheel? Speed of the vehicle divided by radius. Now, this angular velocity of the wheel is nothing but, given that the motor is a hub motor and without gear ratio being simple, the angular velocity of the wheel is nothing but the angular velocity of the motor. Right now, this angular velocity of the motor is further converted into linear velocity, that is basically into radius per second, which I am going to talk about it in the coming thing. Right, and it is now we know the speed at which it is moving, we know the force that is required to move, so we got the angular velocity and we also got the torque, and it is from this torque we derive the power of the motor that is required to drive the vehicle at a desired speed. Right, now I'm going to talk about how do we convert the angular velocity of the motor into the linear velocity of the motor. I'm going to talk about it now. Right, so once you get the angular velocity of it, and you anyway got the torque, calculation from the traction forces that we have done, right? So the speed of the vehicle, and what is the speed that you need? You already have torque, so you adjust So you already have torque. So you adjust the angular velocity to get your power requirement, or you understand what is the power that is required to run at a desired speed, because you already got the traction motors ka torque. We'll continue. Now this is very, very important, guys. But before that, let me. I told you that I'm going to talk about the radians and degrees in a very simplified. So friends, it is interesting, right? You're not boring. It's not boring to you. Come on, I need simple answer. Yes, it is interesting. If it is really interesting. Okay. Now let's again. This is very, very fundamental and very basic. I'm again trying my best to get and explain it as easy as possible. Now, what is one radian? It is very, very simple here. See, this is a complete circle, correct? How many degrees that this particular point covered before it came here? It started here and it came here, right? How many degrees it has covered? Come on, guys. How many degrees it has covered? 360 degrees. Oh, sorry. I'll put the chat box here. Yeah. Oops. So it has covered 360 degrees. 360 degrees is nothing but it is a full rotation. Now let us assume the radius of this circle is 2 centimeters. Okay. The radius of the circle is 2 centimeters. Now assume that I'm starting from this point, and along the circumference of the circle, I'm exactly traveling the same 2 centimeters ka radius. Okay, I started here. The radius is assuming the 2 centimeters. I exactly traveled along the circle for only 2 centimeters. Now, that means this particular thing is called, this particular arch, that particular arch or that particular thing is called radian. So 1 radian is the angle you get when you rotate the radius of the circle on distance on the circumference equal to length of the radius. Now, to do that, what is the angle that is it has to move to get a radian equivalent? What is radian basically? The movement on the circumference of the circle equivalent to that of the radius is the radian. Now this is the distance. This particular curve ka length is around 2 centimeters here as an example. For a point to move this 2 centimeter, you know how much angle it has to transfer or it has to move? It has to move close to around 57.3 degree. Did you understand? Okay. So now, are you here with me? Yes or no? Come on, guys. Type yes or no. Okay. Clear. Clear. Now, 360 degree is equals to what? 2 pi radians, correct? 2 pi r is nothing but the 360 degrees. If somebody completes a 360 degrees, that means that particular thing has completed 2 pi into r distance. This is basically is called what? The circumference. Are you here with me? Yeah. Now come to this. When a circle completes 1 full revolution, that means it has completed how many radians? 2 pi radians. You agree with me? 1 full point. Imagine you take a tire of the wheel. You put a dot here. For this wheel to complete so much thing, 2 pi radians. Okay. So what does revolution per minute means? Revolution per minute means 2 pi radians in per minute is nothing but 60 seconds. And what is pi? Okay. Pi is 3.14. So when you multiply 2 into 3.14 divided by 60, that is basically 6.28 divided by 60, that is 0.628 divided by 6, that basically is 0.10 radians per second. This is how you convert the angular motion of this into the radiant motion. So 1 revolutions per minute is nothing but 0.10 radians per second. Similarly, the inversion of it, 1 radiant per second is nothing but 1 by 0.104 revolutions per minute. So radian is the unit of revolutions measured in SI units. Are you here with me? Simplified? Yes or no, guys? Simple. 1 revolutions per minute is equals to 0.104 radians per second. Yes, we have derived this. Now, let's go back to the previous one. Now, I'm giving you one quick assignment on this particular thing. I want you to quickly do this assignment. Very, very simple assignment. Right? This is basically to give you the clarity between the angular velocity and then the linear speed. This is very, very important. Now, a bicycle is moving at 11 meters per second speed. That means this guy, in 1 second time, how many meters is he covering? 11 meters. So what is his linear speed? 11 meters per second. And then the wheels, that means this particular point is moving at 11 meters per second. Now, the wheel has 70 centimeters diameter. That means roughly 35 centimeters. R is equals to how many? 35 centimeters as a radius. Assume that there is no slipping. Calculate the angular speed of the wheels in the RPM. This is the question. Quickly calculate. See, I've given you the radius of the wheel. I've given you the linear velocity. Calculate the angular velocity of the angular speed of the wheel. Angular speed means that wheel revolutions per minute. Revolutions per minute is the angular velocity, right? You got the linear velocity. What is this? 11 meters per second. And you also have other parameters given. Now calculate the angular velocity of the wheel. Okay. The angular velocity of the wheel is very, very simple. It is velocity by the, so what is the velocity linear speed? Linear speed is 11 meters per second divided by the radius is 0.35 meters. So that basically is 31.4 radians per second. So what is it that we are asked? You are asked to calculate the angular speed in RPM. You are given the linear speed of the vehicle and radius of the vehicle. So we use the formula V is equals to R omega. One rotation. Now, whatever we have done in that particular calculation there, he has repeated the same. Omega is equals to V by R. V is equals to 11 meters per second. Right? And R is equals to 0.35 meters because 35 centimeters is 0.35 meters. It is 31.4 radians per second. Now, how do you convert 31.4 radians per second? You will convert 31.4 radians per second. How do you convert? We have already seen that in the previous thing, right? Radians per second to revolutions per minute. How do you convert? Because radians per second is again the linear measurement of the angular velocity only along the circumference. So that we have seen here in the next slide. Previously we have seen, right? That 31.4. Correct. When you multiply that with 9.5 revolutions, it becomes the, right, roughly 300 revolutions per minute. So that means when a cycle of 11 meters per second linear speed with a 35 centimeter of wheels are moving, that means when the cycle is moving from point A to point B at a speed of, in 1 second, if it is going 11 meters, means in 1 minute, it is the wheel is revolving 300 revolutions. If you want to convert it into seconds, that 300 revolutions, you again convert that divide by 60. That means for this cycle to move 11 meters per second, the wheel has to revolve 5 revolutions per second. Guys, is it clear? The difference, how we got the the relation between the linear velocity of the cycle and then the angular velocity of the vehicle. Is it clear? Come on, guys. Is it clear? Perfect. So we have almost come towards the end of it. I will be giving you an assignment. So let's continue this way. So this is very important. Now we are almost kind of summarizing. Traction power must be the minimum sum of the three forces. What is that minimum sum? Drag force, rolling force, climbing force. Now traction power of the motor is nothing but the traction force Ft into velocity at which you wanted to do becomes your traction power of the motor. Torque required at the motor is nothing but the traction force into radius of the wheel becomes your torque required. We have seen all these I would say combinations elsewhere. I mean already, not elsewhere. We have seen all of these combinations already. Let's continue. So power in watts, again, this quick revision. Power in watts is nothing but force into velocity. Force is nothing but torque by radius. Velocity, again, if you want to convert, it is revolutions per minute by, again, r radius by 9.55. So power in watts is nothing but torque into revolutions per minute by 9.55. These are all the same thing, which is converted into multiple things. So now coming back to this particular thing, same example. Drag coefficient, frontal area, weight, coefficient of friction, tire radius, velocity 1, velocity 2. We found out rolling resistance, we found out gradient resistance, we found out aerodynamic resistance at velocity 30 kilometers per hour and velocity 80 kilometers per hour. Then we got traction force at velocity 0. Then we got traction force at velocity 30 kilometers per hour. We got traction force at again at velocity 80 kilometers per hour. Then we also got the angular velocity of the wheel. That is angular velocity is nothing but the V by R. Again, this V, that 30 kilometers per hour, you will have to convert it into meters per second. Very simple. Kilometers equals to 1000 meters per hour is equals to 60 minutes into 60 seconds. So 1000 by 3600, right? So it is 10 by 3.36, or when you convert it above, it is 3.6. Okay. So that is how you convert kilometers per hour into meters per second. You multiply that particular thing into 3.6, and then only you have to get everything into meters per second when you do it, right? Please understand, most of the JE problems, JE solutions, people lost their marks just because of units, because there are some units that are given, they would not convert those units into the actual formula where the units are derived. Meters per second ke place mein they put kilometers per hour, and hence the answer will be varied by 3.6 times, right? So be very careful. So that's where you get the angular velocity. Now then you will get the revolutions per second. Then you get angular velocity to linear velocity of the motor. How do you calculate? Now, okay, now though I have completed this, let me quickly take the homework, please. Harshita, kindly make a note of it. This is the homework. So in the past homework, you got up to here, up to aerodynamic force, you have got it. Okay. Now, this is the new homework for you. What is the new homework? The new homework is you will have to calculate almost 8 parameters. Parameter now, number 1, please note it down in the chat box, WhatsApp, as I type, Harshita, please. Parameter now is, 1 is, find out the traction force at velocity 0 kilometers per hour, at velocity 30 kilometers per hour, and at velocity 80 kilometers per hour. The first one, traction force at velocity 0, velocity 30 kmph, and at velocity 80 kmph. Question number 1. Question number 2, at a speed of 30 kilometers per hour velocity, what is the angular velocity of the wheel? Question 2 is, what is the angular velocity of the wheel? Question number 3 is, what is the power watt that is exerted at 30 kilometers per hour, 80 kilometers per hour? power? These are the three questions. Okay, let's continue. That is now first assignment. Okay, so you complete that assignment and we will discuss this next week. We'll quickly revise the dynamics, and then we quickly revise the dynamics, and then we will enter into the energy from the battery. So today, what is it that we have learned is basically we have revised different fundamentals of physics, mechanicals from the beginning, right from distance to force, distance to velocity to acceleration to force to energy to power. Then we also looked from electricity, potential difference, power. Then from the then we looked at different forces acting on the vehicle: drag force, rolling resistance, as well as the climbing force. Then we said for the vehicle to move, it has to at least overcome all these three forces. We calculated the forces, all these three forces for two-wheelers, three-wheelers, as well as four-wheelers at velocity 0 kilometers per hour. That is just for it to begin. And if at all it is going at 30 kilometers per hour, what is the force that is required? If we intend to run it at 80 kilometers per hour, what is that required? We looked at for all those three. Then we also converted that linear speed of that particular vehicle into the angular velocity that is required, at the hub motor. The example that we have taken is a cycle 11 meters per second car. We looked at what is the revolutions per minute or revolutions per second. So 300 revolutions per minute. That is how we in the example. So we arrived at that omega, the revolutions per minute at the motor. Then we also looked at the torque required at the motor. The torque required is nothing but the force that is being applied to the vehicle to maintain that particular speed multiplied by the radius of that wheel. You got the torque. So now you have torque, you have angular velocity. You multiply both of them, you will get the power requirement of the motor. That is what this assignment is all about. You find out all those three forces in the previous assignment. Now with those three forces, you find out the traction force at three different levels. And as per the traction force, you find out the angular velocity, again at the three different velocities. And you start multiplying T1 omega 1, T2 omega 2, T3 omega 3. You get three different power metrics. Are you here until now with me? Yes or no? Perfect. Okay, I think this is a great class. How did you like class, guys? Come on. So any specific quick questions? Yeah. Then if there are no questions, then probably what I'll request you, one specific request to make. The request is very, very simple. Please submit your assignments on time. Be punctual. I mean, be very, very particular and punctual when it comes to submitting your assignments. So why EVs mostly use automatic gears compared to manual gears? Simple. Very, very simple. That's mostly for the convenience and performance. Because see, manual gears are always fixed. The gear ratios, gear ratio 1, gear ratio 2, gear ratio 3, gear ratio 4 is always fixed. You do not have a smooth curve and you do not have a smooth ride. And you will have to engage those gears again and again, which is a manual thing. Now, when you have to change the torque, when you have to change the torque and power requirements as per the energy that you take it from the battery, why should you even give those particular manual things? All you need is just change the resistance with which the power is being consumed from the battery, and you will be able to run your vehicle. So manual is not advanced. Automatic and non-manuals is advanced. See, what is advanced? Automate as much as possible. Reduce the manual intervention. That's what is advanced. Right? So the technology goes towards advanced, and then EVs give that particular opportunity because end of the day, it's a mechatronics machine. You can always compose, program, and do everything. With this, this is Rajeev.